So in section 10.1, we discussed limits. We introduced what they were. Remember, a limit is always asking you for what the y value is. And so today's lesson, we're going to talk about infinite limits and limits going to infinity. And so let's take an example that looks like some of the ones we did last time. So what if I asked you to find the limit as x approaches 2 from the right, correct? That's how you read that, of x minus 2. Okay. Notice, just as a side note, the plug-in method doesn't work. Okay, if you try to plug in 2, notice you're going to get 0 in the denominator. Okay, and we're not allowed to have that. Okay, so the plug-in method fails. And also notice we can't simplify this function at all. Okay, in other words, 1 over x minus 2 doesn't simplify. And so I know this probably wasn't your favorite method from last time, but remember we had a third way when both of the methods failed, when the plug-in method worked, when simplifying wouldn't work, we used a table. Okay, and so I showed you one of those last time. Okay, but here's a problem where you actually would have to use a table. So the key is, remember, you want to pick x's that follow the problem. So we want x's to the right of 2. In other words, things that are to the right of 2, but also getting really, really close to 2. So last time we looked at some that were under our x value, but also over. Well, this time all we have to do is look at things that are a little bit more than 2. Notice, why did we choose these? 2.1 is close to 2, right? But 2.1 is even closer to 2. And then 2.001 is even closer than that. Okay? So notice these values approach 2 from the right. Okay, that's why we chose them. We're allowed to choose anything at all that we want for x, and we chose values that approach x from the right. And then we'll plug these in the calculator. So if you have a graphing calculator, I'm going to try to kind of project it here and see if that works. It's a little dark, but just kind of some keys on the calculator. Let me see if I can get that out of the glare. There we go. All right, so we want to plug these values in. So if you do 1 divided by, make sure you put parentheses, 2.1 minus 2. Okay, notice we will get 10. And then we want to plug in the next number, 2.01. Okay, a trick on the calculators is if you push second enter, it will repeat what you just entered. And then you can go back and just edit and make it 2.1 for x instead of 2.01. So this would be 100. And then last but not least, when we plug in 2.001, we get 1,000. Okay, so our point, remember, with limits is to find out what y is doing as x does something. So if we're looking at the pattern here, notice I can't really say they're getting close to anything like we did last time, right? The y values are just getting larger. Okay, and if we continued to make x closer or x closer and closer to 2, these would get still larger and larger. So in this case, if we had to say what the trend for y is just getting increasingly large. So if I want the limit as x approaches 2 from the right of 1 over x minus 2, it's actually going to infinity. But if we're discussing a limit, if the limit is infinity, it means there never was a limit to begin with. Okay, for instance, if I give you my credit card and I say your spending limit is infinity, well, that means I haven't limited your spending at all, right? So if the limit is infinity or negative infinity, we're going to say the limit doesn't exist. Okay. In other words, the graph, as x approaches 2 from the right, the graph is going upwards very sharply to infinity. So when we look at things like this, we're going to go back and kind of do an algebra review real quick. We need to talk about asymptotes. Okay, so this would have been something you talked about in Business Math 1 or College Algebra, whatever class you had before this one. But a vertical asymptote is a vertical boundary line that the graph approaches but doesn't cross. In other words, it gets super, super close to it, but it doesn't actually cross or touch it. Okay, so if we were to graph the function we had above, let's say I told you to graph y equals 1 over x minus 2. So I'm going to go out maybe 4 in every direction here. I don't need a lot of detail with my graph. And so what a vertical asymptote is it's a boundary line. So I show it with a dashed line because it's not actually part of the graph. And then this is actually what the graph of y equals 1 over x minus 2 looks like. Okay, so this is the graph of the function in number 1. Okay. Notice truly visually as we approach 2 from the right, we are going up to infinity, right? So notice, visually speaking, we can verify this claim that we made above with the table method, that as we approach 2 from the right with the function 1 over x minus 2, if we're asking for the y value, picture you're traveling on this line, you're going up sharply, right, up forever and ever. So, of course, we get infinity. And so what we say, I usually abbreviate the vertical asymptote as VA. We say that the vertical asymptote is x equals 2. Because at the line x equals 2, that is the boundary line that the graph won't touch or cross. So we call this the vertical asymptote. Now, depending on what kind of calculator you're using, if you're going to use a calculator to graph this, the newer calculators won't show a line for the asymptote at all. Okay, that'll just show the graph getting close to a boundary line without crossing it. The older calculators, and by that I mean the TI-83s, are actually going to show a solid vertical line here. But you have to know that on the calculator that just represents the asymptote. It's not actually part of the graph. It's a boundary line for the graph. All right, so we can have a vertical asymptote and we can also have a horizontal asymptote. So you could probably guess what that is. If a vertical asymptote is a vertical boundary line the graph doesn't cross, a horizontal asymptote is similar, although there are some differences. So it's a horizontal boundary line that the graph approaches but doesn't cross. But here's where it's different. It's only as x goes to infinity or as x goes to negative infinity. Okay. In other words, it's at the far left and the far right. Because as we go, sorry about that, far right. So as we go, as x goes to infinity, we're traveling to the right. As x goes to negative infinity, we're traveling to the left. Okay. In other words, it doesn't necessarily apply to any middle sections of the graph, only the far left and the far right. So let's look at a picture example of that. So let's say I give you this graph, and let's go up maybe 2 in every direction or out 2 in every direction. So let's draw a horizontal asymptote maybe at 1. Okay, so this would be our horizontal asymptote. This is the line that our graph is going to approach but not cross, but as we go to the left or the right. And let's say that this is my function. Let's say my function crosses here and then just gets really close to that line without crossing it. Okay, so we would say that the horizontal asymptote is y equals 2. Notice for vertical asymptotes, we say the equation is x equals a number because that's how we write vertical line equations. And for horizontal asymptotes, we will say y equals, sorry, not 2, but 1. But we're going to talk about with this graph maybe something we haven't discussed before. So what if I asked you to find the limit as x goes to infinity of this weird graph f of x? So let's label this up here f of x. So we've had limits where we are approaching a number, right? But we haven't had any limits where we're approaching infinity. So don't let this throw you off. This is just saying x is going to travel towards infinity. So in other words, this means, let's go ahead and say this. This means as x goes to the far right. Because if we're traveling towards x equals infinity, then we're traveling to the right. So as we go to the right, so picture yourself an ant on this graph, you're crawling along, you're going as far as you can to the right. What is the y value going towards closer and closer the further out you go? The answer is 1. Okay, and I could ask the same question as x goes to negative infinity. Okay, now as x goes to negative infinity, let's talk about that before we answer it. This is as x goes to the far left. Okay, because if you're going towards x equals negative infinity, you're traveling left on the number line, right? So again, if you're traveling on this curve and you're going as far left as you can go, right, you're going to get really close to y equals 1. Okay, notice that these limits as x goes to infinity and negative infinity give us the same result as we had for our horizontal asymptote. And that's actually always the case. So the horizontal asymptote will only exist when we have the limit as x approaches infinity of f of x going towards some number, and that would need to be the same as what it was doing to the left. Okay, in other words, as we go to the far right and as we go to the far left, we're approaching some number, and that number happens to be the horizontal asymptote. All right, so let's look at a couple examples and see if we can take maybe common graphs and answer some of these more unusual questions. So I want you to find the limit as x approaches infinity of f of x. I'm going to give you a graph in just a bit. And the limit as x approaches negative infinity of f of x. And let's say the graph that I want you to look at is for the function x squared. So y equals x squared. Okay, so the first thing we'll want to do is graph what this looks like. Okay, so an x squared equation is just a parabola. Notice I don't even need a whole lot of details here, and my parabola is not perfect. It doesn't really need to be. So just like last time, it's just going to maybe take you a bit to get used to this notation. So if I ask you for the limit as x approaches infinity of f of x, you need to be able to understand that I'm asking you for what's happening as x goes to the right. Okay, so let's talk about it. So as x travels right, what is y doing? As we go further to the right, y is going up sharply. In fact, y continues to go up, right? So the limit would be infinity. Okay, we talked about before that that means the limit really doesn't exist. By the way, I would want to see both of these. I would want to know whether it's infinity versus negative infinity, but then in the end, the fact that you know that that means the limit doesn't exist. All right, so what about the limit as x goes to negative infinity of this function? So rather than traveling to the right, we're traveling to the left, right? So, or correct, I guess I should say. So as we travel to the left, so picture you're traveling leftward, right? You're traveling towards x equals negative infinity. Then your y value is still going up. So here it's actually equal to infinity or does not exist. Okay, so notice if I asked you about, say, a horizontal asymptote, there really isn't one. There's no boundary line that the graph is approaching as we go to infinity or negative infinity. So we would say none for this. There's no horizontal asymptote. Okay? If you don't get numbers here and here, or if you don't get a clear limit, then it means that there's no horizontal asymptote. All right, so let's look at one more. All right, so these are the things I want you to find. I want you to find the limit as x approaches infinity of f of x. And same thing as last time, I want you to find the limit as x approaches negative infinity. But I want to add an extra one. I also want you to find the limit as x approaches 0 of f of x. And let's say this is my function this time. F of x equals, excuse me, 1 over x. So first, let's get a graph of this. You could use your graphing calculator, or you could pick some x's and see if you could graph this with like an XY chart or something. But this is what f of x is going to look like. It's helpful if you can see a graph. Not always necessary, but helpful. All right, so let's just split this up into a, b, and c. So if I want the limit as x approaches infinity of f of x, just like before, I'm traveling to the right. So as we travel to the right, it actually does look like the y value is approaching something. In fact, it looks like it's getting really close to the x-axis, and the y value at the x-axis is 0. Okay, I know I've said this a lot of times, but remember, the limit is always saying what is y doing as x does something. Okay, so this is asking you as x goes to the left, what is y getting ever closer to? And again, notice it's the x-axis, which the y value at the x-axis is just 0. Okay, so before we go on to part C, that means we do have a horizontal asymptote, because notice we have a left side and a right side that both go to 0. So the horizontal asymptote would be y equals 0. Okay, and that's true, right? I think you can look at this graph and notice, hey, this x-axis is forming a boundary that the graph doesn't cross as we go to the left or the right. But then lastly, let's see if we can figure this out. So the limit as x goes to 0 of f of x. So notice I didn't indicate from what side I'm going to come at 0 from. So notice as we come at 0 from the right, we go up sharply. As we come at 0 from the left, we go down sharply. So there's kind of some confusion, right? Like, should I say positive infinity? Should I say negative infinity? But in both cases, the limit wouldn't exist, right? So again, if you have a limit of infinity or negative infinity, it means the limit didn't exist at all. All right, so I'm going to put 2 stars by this. We're going to use this for the next little section of problems. So if you have the limit as x approaches infinity of anything like 1 over x to the n power, so that would mean 1 over x, that would mean 1 over x squared, that would mean 1 over x to the third, anything like that, the limit will always be 0. And the same is true of the left side limit. If we have 1 over x to any power at all, the limit's always going to be 0. In other words, the horizontal asymptote would always be 0 in these cases. So I definitely want you to remember this, but let's talk about why. It's because 1 over a really large number, think about 1 over a billion. Okay, if you divide 1 by a billion, you get a very, very small decimal. 1 over a large number is always going to be close to 0. Okay, and the reason why I'm saying the bottom is a large number is because x is going to infinity. So picture the biggest number you could think of, and then you're raising that big number to a power. So the denominator is just infinitely large. So 1 over that large number would always get super, super close to 0. All right, so I'm going to show you an example, and then we're going to come up with kind of a strategy on how to do all of these. So let's say that you were asked to find the limit as x approaches infinity of 3x plus 2 over x minus 5. Now, one way to do this would be to graph this function and see what's happening as x goes to the right. But you need to be able to do this algebraically as well. So we're going to use an arithmetic trick. We're going to divide each term by x. So this is going to change into something temporarily uglier. We're going to divide each and every term by x. This by x, this by x, that and that also by x. And I'm allowed to do that because I'm allowed to do anything to the top of a fraction as long as I do the same thing to the bottom of the fraction. So I know you're probably thinking, why would I want to create fractions within fractions? But I promise there's a point. Okay, so arithmetic-wise, we're allowed to do this because we're dividing the top and the bottom by the same thing. The key here is not to leave it looking this ugly. So now we're going to simplify. In other words, we're going to take each of the individual fractions and see if we could write them nicer. Because notice, x over x is 3, or 3x over x is 3. X over x would cancel out. Make sure you remember that that would leave 1 there. So in other words, I really just have the limit as x goes to infinity now of 3 plus 2 over x. And then on the bottom, 1 minus 5 over x. So let's talk about these two guys right here. As x gets infinitely large, okay, so think of, because x is going to infinity, right? So think of the largest number you could think of. Think of a billion or a trillion. If you divide 2 by a billion or a trillion, or if you divide 5 by a billion or a trillion, and remember, infinity is even bigger than that, then these are going to get really, really close to 0. Remember, a limit is what the values is y approaching, and y, the values would be approaching 0 here. So in the end, they're going to essentially go away, and you're just going to be left with 3 over 1 or 3. By the way, your process would be the same for negative infinity. So there is a horizontal asymptote at y equals 3 here. That's because we got an answer for the limit as x approaches infinity. So this strategy that I used is going to be something that we're going to use for the rest of this section. So the goal of finding limits as x goes to infinity or as x goes to negative infinity. The goal is to get as many pieces as we can to go to 0. So I'm going to say as many parts of the problem as possible. We want those to look like some constant, any number, over x to the n power. Okay? And the reason we want that is because this will go to 0 as x gets large. Okay? And honestly, that will work as x gets large in the positive or the negative direction. So what I often have students forget is they try to do the old problems that we talked about in 10.1 with this method, and you can't. So let me just specify that. This method is only when finding limits as x goes to infinity or negative infinity. So if it's still a problem like we did in the past where it says x goes to 2 or 0, you're still going to try all the other methods we discussed before, the plug-in method, the simplify method, the table method. But when you're finding these new limits as x goes to infinity or negative infinity, this is going to be your strategy. You're going to divide all terms by the highest power of x in the denominator. And we're going to ignore any coefficients. Coefficients are just numbers in front of variables. And then any term that looks like what we mentioned above, any term that looks like a number over x to a power will go to 0. So let's try that with a couple. So if I asked you to find the limit as x approaches infinity of 2x cubed plus 4x squared minus 2 over x to the 4 plus 3. Notice we're doing the limit as x approaches infinity, so we would use this new method. So you're going to divide all the terms, each and every one of them, by the biggest power of x that you have in the denominator. So you're going to divide each term by x to the 4th, because notice if you look in the denominator, x to the 4th is the largest power of x we have. So I like to tell my students that these problems temporarily look uglier, but in the end they will look nicer. Okay, so we're going to put 2x cubed over the x to the 4th, and we're going to do that for every single term. So this is the part that might be a little uncomfortable for you, because temporarily, yes, it's going to make the problem look uglier. Okay, so notice I had 1, 2, 3, 4, 5 terms, and I put all 5 of them over x to the 4th. So don't forget this next step. This is the most important step probably. Make sure you simplify. The whole point of this is not to leave it this ugly. We want to simplify. So the x cubed would cancel with 3 of these x's on the bottom, right? So that would leave x to the 1st power. Notice your algebra skills have to be kind of strong here. X squared would cancel out, and that would leave 2 on the bottom. Notice nothing can cancel here, so we leave that alone. If we divide something by itself, it doesn't go away, it leaves 1. And then lastly, 3 over x to the 4th, we can't simplify that anymore either. So probably the pivotal step is this next one, writing the simplified version. So what did we have left after we simplified? Well, we had 2 over x. We had 4 over x squared minus 2 over x to the 4th. And then on bottom, we had 1 plus 3 over x to the 4th. And so here is where we notice that anything, can't spell today, anything that looks like a number over x to the n power, we're going to say goes to 0. So notice that would cover this one, this one, this one, and this one. Okay, all of these are going to go to 0. So in the end, you're going to end up with a big 0 on the bottom, or sorry, on the top, and a 1 on the bottom. And 0 divided by anything is just 0. So remember that what that means we got an answer. So the horizontal asymptote is y equals 0. So if you were to graph this, there would be an imaginary boundary line at y equals 0 that the graph approached as it went to the left and the right but didn't cross. All right, let's try one with the limit as x approaches negative infinity just to make sure we're clear, the method is exactly the same. So when you have the limit as x approaches infinity or negative infinity, your method is the same. You're going to divide each term by the biggest power on the bottom. So look at the bottom. What's the largest power of x we have? We have x squared. That's the biggest thing we have on the bottom. Notice my limit notation stays. So kind of like last time, I continue with the limit notation until the very end. The stage where you can drop that limit notation is basically where you replace a bunch of stuff with zeros. Okay, so notice right here is where we did that in the last step. So on the next step, we didn't need that limit notation. So we divided all four, 1, 2, 3, 4 terms each by x squared. Okay, and then we want to make sure we simplify. Okay, so just go slowly as you need to. So in this one, x squareds would go away entirely. And this one, an x would go away, canceling one of the x's in the denominator. This one on the bottom, the x squareds would go away, leaving just -5. Notice this guy can't be canceled to an x squared. We have to just leave that. So I end up getting the limit as x approaches negative infinity of 2 plus 3 over x over -5 plus 2 over x squared. Okay, and then this step, anything where it looks like a number over x to the n would go to 0. So that covers this guy and this guy. Okay, they're both going to go to 0. And so all we're left with is 2 over -5, or just -2/5. So there is a horizontal asymptote since we got an answer here. So the horizontal asymptote would be y equals -2/5. So keep in mind here that we only use this method when we're doing x goes to infinity or x goes to negative infinity. And really, we just have to kind of practice our algebra simplification. That's probably the biggest part of this. So let's say you do this method and you get some number, okay, some number that is not 0 over 0. In other words, maybe you get 3 over 0, or -5 over 0, or 10 over 0. Those types of results means the answer is either positive or negative infinity. Okay, we're going to look at an example of that in just a bit. But if you get 0 over 0, we discussed this last time, this is undetermined or undefined. Okay, that just means the limit can't be determined with this method. You never stop when you get 0 over 0. You try something different. It could mean you did something wrong. It could mean you didn't divide by the correct thing. Okay, so remember, you're always supposed to be dividing by x to the highest power that's in the denominator, I mean. All right, so let's try this strategy and see what happens here. All right, so we have x to the 6th minus 2x to the 4th, and then over x cubed plus 2x. So we're going to do our same strategy, right? We have a limit as x goes to negative infinity, so we're going to divide each term by the biggest power on the bottom. So the biggest power on the bottom is x cubed. So let's rewrite this. So it's going to be the limit as x approaches negative infinity of all 4 of these terms over x cubed. Okay, so don't forget your simplify step. But this one's going to simplify a little differently. So we still have our limit as x approaches negative infinity step. All right, so let's see what we get. X cubed cancels with the 1 on top and leaves 3 on top, right? This x cubed would cancel with 3 of those, leaving 1x. X cubed over itself is going to leave a remainder of 1. And then here we're going to cancel 1x, which is going to leave an x squared on the bottom. So let's talk about what I have left. I have x cubed minus 2x on the top, and then I have 1 plus 2 over x squared on bottom. So when I go to do my 0 step, as I call it, there's really only one thing that would go to 0. Okay, that would go to 0. So notice we're still left with the limit as x approaches negative infinity of x cubed minus 2x. We didn't get everything to kind of go away in this case. So at this stage, we know the answer is just going to be, by the way, we have a number over something over 1, right? So that's why I put that equation by itself. Something over 1 is just itself. So at this stage, you can't really plug in infinity, but you kind of think about it. Basically, you're just needing to figure out whether it's going to be positive infinity or negative infinity. So if you plug a negative large number in and you cube it, the question is, will it be a positive sign or will it be a negative sign? Because of this cubed power, it would be a negative sign. So we're going to get negative infinity, but remember that means the limit doesn't exist. Okay, if this would have been, say, a 4th power or something, then we would have said positive infinity, because when you raise a really large negative number to an even power, you get a positive value. So, for problems where maybe we don't have fractions, you really kind of just think to yourself that, hey, I'm doing the plug-in method. Okay. In other words, notice this is just a polynomial. There's no fraction. There's nothing to do the same to the top and the bottom to. We don't have a bottom. So in this case, you just need to picture what happens if I plug a really large positive number in and I raise it to the 4th power. Okay, ignore the negative 2 for now because we're doing order of operations. So big number to the 4th power would be a big positive number, but then I'm going to multiply it by a negative 2. So this one's also going to be negative infinity. And remember, anytime we get a limit of infinity or negative infinity, we say the limit doesn't exist. All right, so for the last question of this lecture, before we do that, let's make a statement here. So for polynomials are just multiple termed expressions where x is raised to a positive whole number. So it could be x squared, x cubed, x to the 4th, x to the 12th if we wanted. But for all of those type equations where we don't have a fraction, the limit as x goes to positive or negative infinity of that function is either going to be positive or negative infinity. And then remember, that will mean it doesn't exist. In other words, this is a polynomial, so the only two options were I was either going to get an answer of the limit is negative infinity or infinity. Okay, and in both cases, of course, that means it doesn't exist. So there'll be some on Connect that you can practice like that. All right, so for the last question of this lecture, we're going to look at our first application problem. So this class tries to relate some of these calculus topics to the business field. So we're going to kind of get our feet wet with a basic application problem today. So let's say a company manufactures snowboards and has a fixed cost of $200 per day. And total costs of $3,800 per day. when 20 boards are made. And by the way, you have a Connect question that's similar to this for this week, for this section anyway. So the first thing I want you to do is just an algebra review. I want you to write a linear cost function. Remember, linear functions typically look like y equals mx plus b when we're done with them. So we have a fixed cost of $200, but a total cost of $3,800. So the $200 fixed cost is going to occur no matter how many boards we make. So let's see if we can figure out what the variable cost would be. Now in the class before this one, in Business Math 1, we talk about that variable cost changes, that's why it's called variable, depending on how many items you produce. But fixed cost, just like the name implies, stays fixed. So in other words, we're going to get charged $200 because that's the fixed cost, but then we have an extra $3,600 that came from the fact that we made 20 boards. So what I'm trying to get to is figure out how much each board actually costs the company. So if I divide that $3,600 by 20, then I'll get 180. Okay, remember this would be the cost for each board. Okay, and I need this because this is actually representative of my slope. Remember, slope is a rate of change. So if I had to describe what is the cost changing by each time I made a board, it would be 180. So usually we use capital C of x to talk about cost. Okay, I'm going to say y equals there, but it's going to be C of x equals. And then mx plus b, m is the slope, right? So we just determined the slope was 180. And then b is the y-intercept. So think about what would the cost be if we made no boards at all. We would still incur a cost of $200 since that's my fixed cost. Okay, so let's talk about how we could determine average cost. Like a general equation for the average cost. Okay, so you would need to know two things for the average cost. You would need to know how much total did all the boards you made cost, and then you would need to divide that by the number of boards. So we talk about average cost in Business Math 1, but I know that some of you are coming from college algebra and you probably would have been less likely to talk about that here. So total cost we call C of x. The number of boards we represent with x. Okay, in other words, x represents how many boards we made. So the average cost equation, like if I ever wanted to know what the average cost per board were for however many boards it was that I made, the average cost equation would be 180x plus 200. That's my C of x. And then I need to put that over x. So we're going to talk about average cost at various times this semester. So average cost is always total cost divided by x. And then last but not least, I want you to answer this question. I want you to tell me, what does this average cost function, the one that we just found in part B, I want you to tell me what it approaches per board as production increases. So in other words, if I think about production going up and up and up and up, okay, then what's going to happen to my average cost? So I'm going to underline this phrase. So this doesn't come right out and say that you're supposed to find a limit, but actually that is exactly what we'll need to do. So this is how we write what they're asking for. We want to know what happens as we increase X forever and ever. In other words, as we increase production for the function 180x plus 200 over x. Okay, so now that we know what to do, which admittedly I think is the toughest part of this problem, now we just use our strategy. So we put everything over the largest power of x, right? So I'm going to have 180x over the x, 200 over x, and on the bottom I'll have x over x. So the first thing we do is raise each of these three to the highest, or put those over the highest power that we have in the denominator. And then we simplify. So the x's go away there. The x's go away here, leaving a 1. So let's talk about what we have left. We have the limit as x approaches infinity of 180 plus 200 over x. Notice I didn't write over 1 because something divided by 1 is just itself. But here's my rule, right? As x gets super large, any number over x to a power is going to go to 0. So as x gets infinitely large, this $200 becomes insignificant, is what that's trying to say. And so in the end, the more boards you create, the closer to 180 the average cost becomes. This is the average cost per board. So I like to think of it this way. We had a fixed cost of $200, okay? If we only made 2 boards, that fixed cost of $200 would be much more significant than if we made 2 million boards, okay? If you made 2 million boards, then this $200 is getting divided out to each of those 200 million boards, and it's pretty inconsequential, right? So the average cost is going to approach 180, okay, which notice was the same amount of the variable cost per board.